I'd like to spend a few moments talking about some of the fundamental concepts behind oscillations in waves. You've likely seen oscillatory behavior in nature. If any of you have seen a pendulum where you have this kind of motion, so you're going to have a maximum motion in this direction, and then it's going to swing back around in a maximum motion in this direction, and it keeps repeating itself. That's an example of an oscillation. If you can imagine like a spring, imagine you put a mass on the end of a spring and then you displace it and let it go, and you see an oscillation. If any of you have observed waves on water, you're seeing an undulation of peaks and troughs and peaks and troughs. And so those oscillatory patterns can be described with mathematical wave functions. And I want to emphasize that these waves are descriptions of patterns that repeat themselves. But it's not like a wave is like some magical new thing that you were introducing into the cast of characters that make up the universe. A wave is a description of the things we've already seen doing the waving. And so this is kind of like how sometimes when people learn about circular motion and they learn about the concept of centripetal force and centripetal acceleration, they think that that's some new different thing to learn about. But really, it's just the old cast of characters, i.e. the forces that we've already been introduced to, that happen to supply the centripetal force necessary for an object to remain in circular motion. So for instance, like if I'm swinging something around in a circle and it's tied to a string, it's not like I'm invoking some magical new centripetal force to make that happen. I'm using the tension in the string that happens to be oriented towards the center of the circular trajectory and supplying the requisite centripetal force. So the centripetal force is a description for how forces we've already encountered happen to be oriented such that they allow circular motion to take place. And so similarly, when we talk about waves, we are describing things in nature that we've already been introduced to, but these things happen to be doing the waving. They happen to be working in ways in which the patterns that we observe with them can mathematically be described with wave functions. And these patterns are periodic. They repeat themselves. And so there's different flavors of waves, i.e. there's different ways in which the constituents of nature can do the waving. And so I mentioned a moment ago with water, and if you were to throw a rock into a pond, you would see these ripples, these undulations, these peaks and valleys, if you will. And it turns out that when you see that, you have this perception that the water is moving out as the wave propagates. But in reality, what's happening is that if you can imagine like a little piece of water gets disturbed and it kind of goes up and down. And then next door, a piece of water goes up and down. And the next door, a piece of water goes up and down. And so you have this propagation, but actually the propagation is propagation of motion that's up and down, even though the propagation is going outward. So in other words, the motion itself, the thing that's doing the waving, the bits of water, if you will, that is perpendicular to the actual wave propagation, i.e. the pattern's propagation. And so if you were to actually keep track of a little piece of water, when you look at a wave, you would think, oh, well, it's just surfing the wave. It's just moving along with the wave. But in reality, it's actually just going up and down. Its neighbor's just going up and down. Its neighbor's just going up and down. And so the water more or less stays where it is because its motion is actually perpendicular to the motion of the pattern that we're observing. And so that's called a transverse wave. A transverse wave is when the things that are doing the waving are perpendicular to the actual direction of the propagation of the wave pattern. There are examples, though, of where the things that are doing the waving are absolutely moving in the direction of the propagation of the wave pattern. And a perfect example of this is sound. Like when my mouth opens and makes a disturbance in the air, there's a pressure disturbance. That pressure disturbance then causes a pressure disturbance to the air next to it, to the air next to it, to the air next to it. That's how sound waves propagate. So when the thing that's doing the waving, in this case, the pressure disturbance is in the air for sound, and that happens to be in the same direction as the wave pattern's propagation, that's called longitudinal. I mentioned the spring earlier. where we disturbed the spring and the spring was going back and forth, you can imagine that the spring, the thing that's doing the waving, is actually in the direction of the motion. So that would be another example of longitudinal. Going back to transverse, classic example of this, maybe some of you have had the experience of being like in a stadium or an arena where the fans, quote unquote, do the wave, where what they do is essentially you have these different sections, right, that are having a pattern develop. But what's happening is that, so a certain section, when it becomes their turn, everybody stands up, right? They put their hands up and then they sit back down. And then the section next to them, everybody stands up, yay, and then they put their hands back down. And so this keeps going around the stadium. Now what you are observing is you're observing a pattern that looks like a wave going around the stadium. But in reality, each section is just going up and down, up and down. And so if your motion is perpendicular to the direction that the wave pattern seems to be propagating, that's the example of transverse. So like when people go section by section in a stadium, going up and down, and then the next section goes up and down, that's not unlike the wave patterns that we see in water. So waves are patterns. They're patterns that repeat themselves. They're patterns where there are peaks and amplitudes. And then you have, say, a peak amplitude and a valley in amplitude. And the peak and the valley have the same like magnitude, if you will, but they're in opposite directions, right? So with a wave, you can imagine you have like this peak, and then it goes down to a valley, and then it goes to another peak, and then to another valley. And so there's a term that we use called the period, and the period describes how much time elapses. So if you were to time a wave-like phenomena from peak to valley back to peak, all right, so it's gotten one cycle. It started at peak, it went to its valley, and then got back to its peak again. So it's peak, valley, back to peak, okay? That's one cycle. The first time it gets back to where it originally was, peak, peak, it's gone through one cycle. And so the amount of time that elapses for one cycle to transpire, that's called the period of a wave. And so then we can also think about, well, if I start at a peak, go to a valley, and then go to another peak, well, how much distance have I covered in going from peak to valley back to peak? In other words, how much distance have I covered in one cycle? We call that the wavelength. The wavelength is the amount of distance that's covered in one cycle. And so then you could probably guess that there's a relationship between how much distance is covered in a cycle and how long it takes for a cycle to transpire. And so think of how wavelengths might differ. You could have one wave where you have a peak and then a valley and then a peak. You could have another wave where you have peak valley, peak valley, peak valley, peak valley, peak valley, peak valley. All right, those are both waves, but in the latter case, you have a much shorter wavelength than something like that. So when you have a much shorter wavelength, assuming both of those waves were propagating at the same velocity, it would take a lot less time for a cycle to complete itself, not as much distance to travel in one cycle. So we would say that the wave where there's a much shorter wavelength, there's many, many, many more cycles per second, we'd say that has higher frequency. So if a period is how much time it takes for one cycle to transpire in a wave, you can think of frequency as the reciprocal of the period. In other words, 1 over the period. You could think of the period as the number of seconds per cycle. You can think of the frequency as the number of cycles per second. So if you have a shorter and shorter and shorter period, i.e. it takes less and less time for a cycle to complete, you're having higher and higher frequency. So the wavelength is related to the frequency as well then, because if you have, say, a lot more distance to travel in a cycle, then you're going to have a lower frequency than if you have much less distance to travel in a cycle. So think of it like this. You have some waves where you have a longer wavelength, that is, for a particular cycle, there's more distance to travel. And then you have some waves that are more like squiggly, like there's lots and lots and lots and lots and lots of cycles taking place. And so something that has a much longer wavelength has a lower frequency. And something that has really short wavelengths has a much higher frequency. So that's an important thing to know about waves. High frequency means typically shorter wavelengths. Low frequency typically means longer wavelengths. So there's an inverse relationship between frequency and wavelength. And once again, if we have a clock and we're trying to time how many cycles transpire in a second, that's going to be the period. All right. If we go in 1 second, we go from peak to valley to peak, then the period is 1. If in 1 second we go peak, valley, peak, we've done 2 cycles. So the period there would be half of a second. And then to get frequency, so if you imagine the period is cycles per second, frequency is the number of cycles, the amount of time per cycle. So it's the reciprocal. And so the unit of period is going to be seconds. The SI unit will be seconds. And then frequency, which is hertz, is going to be 1/second. You can think of frequency as the number of cycles per second. Another important thing to know when it comes to waves is how waves, when they crash into each other, what happens. And so this is the phenomena of interference. And so for simplicity, imagine 2 waves. And imagine each wave has its peaks and its valleys. We could determine what its wavelength is, that is the distance over 1 cycle. We could determine what its period is, that is like how much time it takes for 1 cycle to transpire. We from that can figure out what the frequency is. It's the reciprocal of the period. And so for simplicity, imagine that we have 2 identical waves. And those 2 identical waves have exactly the same peaks and exactly the same valleys, exactly the same wavelength, exactly the same period, exactly the same frequency. And let's say that those 2 waves crash into each other. So what happens here is that you add the amplitudes of the waves. So like for instance, if they're completely in phase with each other, all of the peaks are going to align with all the peaks. All the valleys are going to align with all the valleys. So for simplicity, let's say that the amplitude of wave 1 at maximum was 7. Well, that means if the other wave is identical, the amplitude at maximum for that wave is 7. So then you can imagine a composite wave, a super wave, if you will, which is the addition of the 2 waves that are crashing. So if each individual wave had a maximum amplitude of 7 and they were perfectly in phase, then the resultant wave would actually be 7 plus 7. You would actually add the amplitudes of each of the individual waves, and then you would have an amplitude of 14 for your resultant wave. Similarly, like if these waves are completely in phase, same wavelength, same frequency, same period, same amplitude, well, the valleys would be minus 7. Okay, the valleys are going to have the same magnitude. They're going to be in the opposite direction of the peaks. And so if the 2 waves crash into each other, then the peak of one wave minus 7, the valley of one wave minus 7 plus the valley of another wave minus 7, you're going to have a minus 14, right? So if you can imagine, if the waves looked like this and they were perfectly overlapping with each other, the resultant wave would have a greater amplitude, right? So a much higher peak and a much lower valley. And it would be precisely because the amplitudes of the two waves that crashed into each other added up to make a super peak, right, which is twice the amplitude of each of the individual peaks, and a super valley, which is twice the amplitude of each of the individual valleys. So that's how waves will interfere with each other. Now, sometimes waves aren't in phase with each other. So imagine you had one wave that was like this, and another wave where its valley corresponded to when the other wave had a peak, and when it has a peak, it corresponds to when the other wave has a valley. So that would be a situation where the waves are completely, they're what are called 180 degrees out of phase with each other. And that means that the peak of one corresponds to the valley of another. So imagine the same two waves now, but now they're 180 degrees out of phase with each other. So the peak of one, with amplitude 7, would be added to now the valley of the other, which is an amplitude -7. So what's 7 plus -7? It's 0. And similarly, the valley of the first wave is -7, but it corresponds now with the peak of the other wave, which is +7. And so that would be 0. And it turns out any other part of the wave, when you add the two together, if they're 180 degrees out of phase, the addition of the amplitudes is 0. And so what you would have, so if you have one wave, peak, valley, and then another wave, valley, peak, if you added them together, if they crashed into each other and they were perfectly out of phase with each other, the addition would be a flat line. It would be 0. They would constructively interfere with each other, totally cancel each other out. So in nature, we see a lot of situations where there are waves that are in combination of constructively interfering with each other in ways that actually make larger waves, and in other cases, times that completely cancel the waves out. And so let me leave you like with an example. This would be an example with respect to sound. So let's say that, imagine like I'm on a stage, and like imagine each of my hands represents a speaker, okay? And now imagine like you're like in the audience, you're looking at the stage, and imagine I'm like playing music on the stage, it's coming out of these two speakers. Now, if you're sitting like right in the center of the auditorium, then if you can imagine the distance, if you were to draw a line from you to this speaker or you to this speaker, it would be an isosceles triangle. Like the distance that's traveled with the sound waves from each speaker is the same when it gets to you. So if the distance between each speaker is the same, and when the sound comes out of the speaker, if the waves are in phase with each other, and again, that means that the peaks align with the peaks, the valleys align with the valleys, then if they're traveling the same distance, they have the same velocity, they were in phase when they left the speakers, then you better bet that when they get to your ears, they're going to still be in phase with each other. And so they're going to combine, and you're going to have this amplification of sound. However, same speakers, but imagine that you weren't sitting center stage, okay? Imagine you were a part of the auditorium that was like, say, closer to this speaker and further away from this speaker, okay? Well, that would mean that the distance that's covered between this speaker and where you are is a lot less than this speaker. So if there was a difference in the distance that needs to be covered when the sound emerges from each of the speakers, then that difference in distance is crucial in determining when the waves constructively or destructively interfere with each other at the location of interest. What was the difference in distance, and how does that compare to the wavelength? Because, for example, again, two speakers, when you're at the center of the room, they travel the same exact distance. And so if they're in phase, when they leave the speakers, they're still in phase. However, if you instead move, say, you're moving to, say, something that's closer to this speaker, then that means that the distance from this speaker is greater to you than the distance from this speaker. So then the question is, what is the difference in that distance? Hypothetically, let's say that the difference in that distance was just one wavelength. Well, these waves repeat themselves. So if a wave is going to repeat itself, even though the wave from this speaker had to travel farther, if it was just a difference in distance of one wavelength, then it would go one additional wavelength, but it would still be in phase with the wave that left this speaker. Okay, it went a little further, but remember, they repeat themselves, so when they get to your ears, it's like they're still exactly in phase with each other. But think of it like this. What if the difference in distance was half of a wavelength? Well, that means that because it's a half wavelength difference, then the wave that leaves this speaker, because it has to travel 1/2 wavelength more than the wave that leaves this speaker, when the wave that leaves this speaker hits your ear, it's going to be 180 degrees out of phase with the wave that left this speaker. So now those waves would actually constructively interfere in a way where they cancel each other out, because they originally left the speakers where their peaks matched the peaks, the valleys matched the valleys, and now because of the difference in distance that the waves have to travel, because you don't have this symmetry in your position where you have the speakers and how far are you away from the speakers, if you're closer to this one now than you are this one, there's a greater distance the wave has to travel. And if that difference in distance corresponds to a half of a wavelength, or 1.5 wavelengths, or 2.5 wavelengths, or 3.5 wavelengths, then it turns out it's out of phase. And so you would have a dead zone. You would have an audio dead zone. And that's why in an auditorium, there's going to be locations in the auditorium where the sound is going to be better or worse. Because I'm giving you extreme examples of when things are completely in phase or completely out of phase. You could probably imagine that there's differences in distances between two speakers that isn't precisely a whole wavelength or half a wavelength. Maybe it's just like a third of a wavelength. So there's going to be combinations of interference where the waves are going to be adding each other up or destructively interfering each other out. So that's the concept of interference, and it's a concept that's going to come in handy when you start to think about things like the phenomena of diffraction. And it turns out that interference is going to allow us to think about, like, if you were to have two waves on water crash into each other, what would happen? And when you talk about objects in the universe that go through oscillatory motion, like imagine like two particles and they're in a bond and there's a vibration. Well, it turns out that that bond vibration can be described with a frequency. There's that term frequency again. And it turns out that, and this is not within the scope of the first semester of introductory physics, but when we get into the second semester of introductory physics, we get into more modern physics, we find that with electromagnetic phenomena, which is the oscillation of electric and magnetic waves, that it turns out that the frequency of the electromagnetic wave vis-a-vis the frequency of molecules and their vibrations, it turns out that there are things that electromagnetic waves will pass through and not even interact with if their frequencies aren't similar. And similarly, if their frequencies are similar to the electromagnetic radiation incident on it, then it will interact. And I'm not expecting you to have a crystal clear idea of this right now, but the idea of waves is powerful when you get into modern physics and being able to explain things like why the sky is blue and why sunsets seem more orangish red than the blue sky. It also has to do with the concept of waves and the concept of frequency. And so now we're laying the fundamental building blocks for those concepts. So one last time, a wave is a pattern. You've been working with wave functions already in dealing with sines and cosines with vector decomposition. And so a wave is a mathematical description of a periodic pattern. And by periodic, it means that there are cycles that repeat themselves. And so the amount of time it takes for one cycle of a wave to transpire, that is the period. Frequency is the number of cycles that transpire per second. The wavelength is the distance that's traveled with one cycle. And so you can imagine these ideas are related to each other. And in general, the longer the wavelength you have, the lower the frequency. The shorter the wavelength you have, the higher the frequency.